The Willamette River flows through the heart of downtown Portland, Oregon, linking the city and state to the world. Portlanders enjoy the river as their playground, visiting its waters for sailing, kayaking, and fishing. Native salmon run through the river to their spawning sites, and waterfowl make their homes along its banks. Portland has struggled to keep the Willamette River clean. Portland's combined sewer system drains both stormwater runoff and sewage into one pipe that heads to the treatment plant. While the system worked fine in dry weather, rainstorms overwhelmed it, causing overflows to spill into the river. Portland is well known for its winter rain, lots of it. The combined sewer overflows, known as CSOs, dumped billions of gallons of untreated stormwater and raw sewage into the Willamette River every year. Bacteria from the sewage and oils from the street polluted the river and generated health hazards.
In 1991, the City of Portland entered into an historic agreement with the Oregon Department of Environmental Quality. It committed the city to a 20-year effort to clean up the Willamette River and the Columbia Slough. To do this, the city agreed to add treatment capacity at the treatment plant, to work aggressively to take stormwater out of the collection system, and to do what was necessary in building storage and tunnels along the Willamette River.
In 2001, the city tackled the problem with a solution that would fundamentally change the way wastewater is managed. A 14-foot diameter sewer pipe would intercept the overflows before they entered the river, store the water after a storm, and deliver the wastewater to a pump station and the existing treatment plant.
For the design of the West Side project, we went through a very competitive procurement process because we wanted to find the most qualified design firm that we could, since this was the largest project the Bureau had ever attempted before. We set up a separate project office with the designer and city staff to work together as one dedicated design team. We wanted to combine the city's knowledge of the project with the consultant's knowledge of tunneling and deep shaft work.
Parsons Brinkerhoff led the design of the project, and Jacobs Associates provided construction management services. Known locally as the Big Pipe, the West Side Tunnel, along with a similar pipe to be tunneled on the east side of the river, would reduce CSOs by 94%. Impregilo, the largest Italian civil contractor, and its American sister company, S.A. Healy, formed the joint venture that was awarded the West Side CSO contract in 2001.
We brought them on board into the design office with ourselves and Parsons Brinkerhoff, and the three firms together worked on design review, doing estimating, doing a risk analysis, planning all the construction for the project. It's very unusual to have the construction contractor working together with the design consultant and the owner before construction starts. That's what made this unique. It proved to be a major advantage in that we got the benefit of the contractor's expertise before the design was done. The construction contract itself was a cost reimbursable with a fixed fee. Labor, equipment, and materials were paid as reimbursable as they accrued, and the fee was a fixed number over the life of the contract, which included all their management costs, overhead, and profit, and was paid as a percent complete. And the purpose of setting it up this way was to have a joint risk-sharing arrangement, whereby if we could get the project done correctly the first time, we would get the best value for the dollar.
A strict control of the schedule and costs was essential to monitor that the project was executed on time and within the budget. Impregilo Healy assembled a team of uniquely qualified people from across the USA and around the globe to tackle the engineering and construction challenges. 12 different nationalities were represented in the workforce. The design of the Big Pipe follows the path of the river, intercepting existing overflow lines along its route. The tunnel heads under the Willamette River, connecting to the pump station where wastewater is pumped uphill to the treatment plant. The construction had to take place in the dense urban corridor of downtown Portland. By mining the tunnel, the 4-year project progressed largely unnoticed from the city's streets. However, the geology of the area presented obstacles to traditional mining methods.
This is the cutter head for the North Drive tunnel boring machine. Each tunnel boring machine is designed specifically for the geology that will be encountered in the tunnel. In this case, the geology consists of sand and silt and gravel, with some large cobbles and boulders interspersed within. The tunnel is also under 100 feet of water pressure. So the material is very saturated. It will run if unsupported.
The solution to these challenging conditions was the Slurry Shield Tunnel Boring Machine, or TBM, produced in Germany by Heron Connect.
The tunnel boring machines used on this project are the first use of this technology in the United States.
Excavation and construction of the tunnel is protected within the shield of the tunnel boring machine. Bentonite slurry acts to both support the excavation face and transport the spoils back to the surface. Concrete precast liner segments make up the rings of the pipe. These segments are erected within the shield of the TBM and extruded out the back, leaving the fully supported tunnel behind it. To move forward, the TBM pushes off of the completed pipe rings. Grout is injected around the segments to seal the exterior of the tunnel. Using this method, there is never a gap in the construction process where unstable earth could collapse into a cavity and endanger workers. The largest section of the Big Pipe project is mined in 2 drives, both starting from the Nikolai shaft. The TBMs are lowered into the shaft 120 feet below the surface. The first drive heads north under the Willamette River to the confluent shaft and pump station. The second TBM heads south along the river, through downtown to the Clay Street shaft. South of Clay, smaller micro-TBMs complete the full length of tunnel. The first step in the project is to excavate shafts along the route. Subcontractor Bencor Petrofon Pacchiosi constructs the concrete diaphragm walls of the shaft, utilizing clamshells and hydromill equipment.
Slurry walls are named because protection of the excavation is done by a bentonite slurry. So essentially a crane will excavate a trench in a series of panels around the circumference. The trench will be excavated to full depth, and to hold the trench open, a bentonite slurry is pumped into the trench. It forms a filter cake on the walls of the excavation so it doesn't collapse.
A rebar cage is assembled for reinforcement within each wall panel, which is then filled with concrete. This process is then repeated panel by panel around the circumference of the shaft to form a complete cylinder. To construct the bottom of the shaft, the Pellegrim's diving team is brought in for underwater work. The divers prepare the surface of the shaft walls, which will tie into a rebar cage used in the Treme plug. The water in the shaft is dirty and dark, and the divers routinely work at depths of up to 130 feet. High pressure limits the periods that they can safely work to 45 minutes at a time. It is not a job for the faint of heart. The shaft is now ready to receive the rebar for the concrete Treme plug, which will be placed underwater to form the bottom of the shaft. Once the slab cures, the shaft is ready to be pumped dry. The Treme plug is an elegant solution to cutting off the groundwater in the smaller shafts of the project. The pump station shaft, however, requires a different approach.
The shaft itself is 150 feet deep and 135 foot in diameter, making it one of the largest soft ground shafts ever constructed here in the United States.
Due to its large dimensions and depth, a different engineering approach was necessary at the pump station. The bedrock lies 320 feet below ground level. Several options were considered for the construction of the water cutoff. The selected solution was to construct a jet grout curtain with large diameter columns extending from the bottom of the diaphragm slurry walls into the bedrock below. The columns overlap, creating a watertight seal. Such deep jet grouting has been implemented in only a few projects worldwide. The jet grout curtain seals the shaft to the bedrock, enabling dry excavation. The enormous size of the pump station shaft requires the construction of an interior concrete lining for structural rigidity. Multiple crews work around the clock to excavate and reinforce the pump station shaft. Across the river, preparations for mining have begun. In the spirit of Northwest exploration, the two TBMs have been named Lewis and Clark. The first segments of Lewis are lowered into the Nikolai shaft for assembly. For the crew, it's an exciting beginning.
Today is a key date for the starting of the real tunneling in the project.
It takes a full month to assemble the tunnel boring machine and all its trailing gear. Nearby, Imprezilo established a plant to produce the concrete ring segments that make up the pipe. Manufacturing on site ensures quality control of this crucial process. Each precast piece is manufactured in exact, uniform dimensions to ensure that the ring fits together properly and is strong enough to withstand the pressure 150 feet below the surface.
The really important thing it's the consistency. You need to be able to every day make the same thing.
The design of the segments is a complex task, as it must take into account many factors of installation, as well as the final conditions of the tunnel. All of the ring elements, the concrete forms, gaskets, bolts, and connectors must be engineered together to guarantee a robust and watertight tunnel design. When the assembly of the tunnel boring machine is complete, the first concrete segments are lowered into the shaft and placed into position in the rear of the machine. The North Tunnel boring machine is ready to begin its 4,000-foot journey. Santa Barbara, the patron saint of miners, extends her protection to the men and women working underground. As the TBM mines, 300 feet of supporting machinery will ride in cars behind it, pulled along on rail lines laid down in the newly formed tunnel.
We are 120 feet below the surface, about 100 feet below the Willamette River, and right now we're in the control cabinet of our north machine.
Additional trailing gear includes motors, power transformers, and grout. Cranes and conveyor belts maneuver the precast pipe segments to the TBM shield. In the last car, crews work to install the utilities feeding the TBM.
The air we need, the water, the slurry coming in, the cuttings going back out. It's quite an elaborate process even behind this machine getting everything to us that we need.
Bentonite is pumped from tanks on the surface to the face of the machine as the cutting head spins. The operator uses compressed air to finely control the pressure of the bentonite slurry. The control of the face pressure is fundamental for the support of the excavation phase at the head of the TBM. The TBM's position underground is determined using a laser guidance system. Its precise location is displayed over the designed route of the tunnel, and the operator makes adjustments accordingly to steer the machine. The mined soil mixes with the bentonite slurry and is pumped to the separation plant on the surface. Here, the solids are separated, and the bentonite is returned to the TBM face to be reused. The excavated solids are loaded on a barge and tugged upriver to Ross Island. The soil itself has helped to restore the island, creating shallow water and wetland environments along the Willamette River. These shallow waters are crucial habitat for birds and endangered salmon. With the northbound drive well underway, the second TBM is lowered into the Nikolai shaft and assembled. This machine, known as Clark, is tackling a much longer drive of 14,000 feet. Clark will head south along the river and through downtown. While the mining operation continues, excavation and reinforcement of the pump station shaft is nearly complete. The crew has reached the final depth, 150 feet below the surface. They prepare a rebar mat for the 12-foot thick concrete base slab. 321 days have passed since the northbound tunnel boring machine began its journey.
We got about 1.5 to 2 foot to go.
Today, the TBM Lewis is expected to hold through the slurry wall of the confluent shaft. The anticipation of the crew is palpable.
Keep the bed 9 level at 0. Bye. It's a very exciting moment to hold through on any tunnel project. It's a lot of hard work, a lot of dedication to a project of this magnitude. Guys have worked 7 days a week, long and hard. Good job. Good job. Today is a milestone in our operation because we have successfully mined under the Willamette River.
The final drive for Lewis is a short 120 feet to the pump station. When completed, the pump station will be a 4-story underground structure that will house the pumps and motors used to deliver wastewater to the treatment plant. While crews pour concrete on one side of the shaft, the other side is expecting the arrival of the TBM Lewis. In total, this northbound TBM completed a 4,000-foot tunnel, mining for 173 days and averaging 22.5 feet per day. The pump shaft marks the end of the line. The cutter head is separated from the machine and hoisted out of the shaft.
The construction of the pump station is a large project in and of itself. The interior of the pump station basically consists of 4 levels underground, and each of those levels has walls associated with it and floor slabs. We have many places where we're pouring 40-foot high lifts, which means we're bringing in lots of concrete and lots of steel. Extensive planning goes into each of these pours to ensure that each of the workers are safe and that the operations are continuous while we're doing the work. By ensuring a continuous flow of concrete to the project, we ensure that in the long term we're going to have a better quality product both in terms of strength and durability. Over the course of construction for the Swan Island Pump Station, we've poured over 43,000 cubic yards of concrete and tied over 5 million pounds of reinforcing steel.
Other shafts along the route of the tunnel are also built up with internal concrete structures. Each of these shafts connects the existing sewer and the tunnel, as well as serving as an access point for inspection and maintenance of the finished pipe. Next to each shaft lies an existing sewer overflow pipe that empties into the river. Workers excavate these existing sewer lines and build diversion structures to channel wastewater into the new big pipe. "21 months after it began its journey, the southbound TBM holes through the Clay Street shaft, completing a drive of 14,000 feet and marking the end of mining operations for the project. The job site at Clay Shaft is packed with people who are excited to be there for the big moment.
We're 2 months early, so it's both satisfying and a rewarding moment to make it here.
All of the preparations that went into mining the tunnel are now reversed. Trailing gear and miles of pipes carrying utilities to the TBM are hauled out. Rail lines are pulled up, and the sewer pipe itself receives final surface patches. At Swan Island, the crews are finishing all of the elements to create a working pump station. An operations and maintenance building is constructed adjacent to the pump shaft. Electrical and ventilation systems are installed within the pump station, and the wet well is sealed with a finish coat that will protect the concrete from corrosive gases. 4 pumps are put in place on the lowest level. The smaller pumps will pump 11,000 gallons of wastewater per minute uphill to the treatment plant. During storm events, the larger pumps will kick in, delivering an extra 60,000 gallons per minute. Powering these workhorses are 2,000 horsepower motors, fueled by a dedicated electrical substation. Inside the operations and maintenance building, technicians and engineers gather to see all their work from the past 4 years put to the test.
This is the test where we really run the software, we really run the pumps. We make sure that it does what it's supposed to do. It's really gone extremely well. We've been running the pumps in automatic for days and days and days. It can pump a lot of flow.
This was an enormous project to undertake. We encountered some very significant challenges during the course of this project, any one of which easily could have set us back on schedule and budget. But through this one-of-a-kind partnership between Environmental Services, Impergy-Lohealy, and Parsons-Brinckerhoff, the project came in ahead of schedule and under budget. It was really a monumental accomplishment.
I'm very pleased and honored to turn this monument over to the people of Portland today.
2, 3.
The West Side Big Pipe project and the Swan Island Pump Station were completed on time and on budget. This met all of our regulatory requirements that were set by the Oregon DEQ. It also has resulted in the removal of billions of gallons of pollution from the Willamette River. Next is the East Side Big Pipe project. When it's completed in 2011, this will complete the 20-year program that was agreed to back in 1991. It will also mark the conclusion of the largest construction project ever undertaken by the city of Portland, and it will result in a cleaner Willamette River, one that this community can enjoy for many decades to come.
The tunnel extends nearly 5 miles, and yet the evidence of its very existence is hidden underground. It is a cleaner river that attests to the ingenious design and years of hard work. The ecosystem, the wildlife, and the people of Portland will reap the benefits of a clean river for generations to come.